This Riemann sum example is going to be a little bit harder since we can't actually find the area under this curve using geometry. So we're just going to establish the area, make sure we have the answer first by actually integrating this. So I'm going to find the area. I'm going to anti-differentiate this into x cubed over 3 plus 4x. And I'm going to evaluate this from 0 to 2. Plugging that in, I'm going to end up with negative 8 over 3 plus 8 minus 0. And that's going to give us 24 over 3 minus 8 gives us 16 over 3 units squared. Okay, so that's going to be the exact area. So let's just first of all establish the expression for our area or for the rectangles using n. So we have our x squared plus 4, negative x squared plus 4. That negative, the x we need to replace with some expression for x. So for every delta x that I shift over, okay, I'm going to be moving my x coordinate over. So my x coordinate is going to be based on k times delta x. So however many k just represents how many spots I'm sliding over, and it's going to be k times delta x. Now I need to establish what delta x is. For that, I need my interval. My interval width is going to be 2. So that's my interval width. And so my delta x is going to be the interval width divided by n. So delta x is equal to 2 over n. So that's what we have here. I've shown my delta x going to 2 over n. Okay, the interval width divided by however many divisions I have. My x value here in this expression, this x value here, is going to be k times delta x. Well, delta x was 2 over n, so this k expression then represents the x variable to allow me to calculate the height of each of those rectangles, individual rectangles. And then I'll multiply it by 2 over n, which is delta x, and then I'm going to sum them all up from k equals 1 to some n value. Now, again, if n is finite, we're just calculating a whole bunch of Riemann sum rectangles, but we're going to let n go to infinity, and this allows me to go from the Riemann sum to the integral. And I should be able, if I apply this, I should get the same area, 16 over 3. Okay, so to do this, again, I need to simplify this expression a little bit, and I need to tease out some parts. And again, I'm going to go back to those formulas. These formulas here, I'm going to have to rely on these formulas to be able to evaluate this limit. And this is, again, the long way of doing things. So we generally will not do this. In fact, it's hard to do for other examples other than these more basic ones. Okay, so let's go ahead and simplify this expression. So I'm going to do the limit as n approaches infinity, k equals 1 to n, and this expression now becomes negative 4k squared over n squared plus 4 times 2 over n. Okay, I'm going to multiply that in, so limit as n approaches infinity, and this expression now becomes negative 8k squared over n cubed plus 8 over n. Okay, so I'm going to factor out my n in my constant terms. So I get negative 8 over n cubed And then I'm going to have to sum up k squared. Now, this is, I have a formula for. Okay, so my formula just happens to be this uh, n times n plus 1 times n 2n plus 1 divided by 6. So this one here, I'm going to need to make use of that one. Okay, I'll do that in the next step. And I need to simplify the other part out. So plus, I'm going to factor the 8n out. 8 over n. And I have from nk equals 1 to n of just 1. And we already established that one is equal to n, because that's just going to be 1 plus 1 plus 1 n times. Okay, so then I'm going to sum up this formula. So limit as n approaches infinity, negative 8 over n cubed. And I'm going to replace this summation with the formula. N times n plus 1 times 2n plus 1. Now again, without this, having this formula, I can't actually sum up that expression. But since I do have this formula, I'm going to use that formula and replace it with the sum of k squareds. Plus 8 over n, and this just becomes, using again the formula, the sum of 1 n times is just going to be n. Okay, so I'm going to expand this out, cancel out some terms. I can see that these n's are going to cancel out, so I'm just going to have 8. And then this expansion here, this is going to be a little bit messy, but the limit as n approaches infinity, negative 8 over n cubed. Okay, I'm just going to put the 6 over here like this. And then this is going to expand out to 2n cubed plus 3n squared. When I FOIL the binomials out, multiplied by n, plus 1 times 1 is 1, times n is going to give me the n here. That's all going to be over 1. I might as well leave that 6 in here. Okay, then we can simplify some terms. Plus 8. So the limit as n approaches infinity, I'm going to end up with negative 16 n cubed over 6n cubed. Okay, so that's going to simplify to negative 8 over 3, plus all these other terms are going to have a larger degree of n in the numerator, so in the denominator. So negative 24, I'll make this minus 24n squared over 6n cubed. Okay, so you can see that we're going to have an extra n left over in there, minus 8n over 6n cubed. Okay, so that's going to cancel out. I'm going to be left with squared there, plus 8. I'm going to now apply my limit. So this becomes, when I apply my limit, I get negative 8 over 3, minus this becomes 24 over 6 times infinity. Well, that's 0. Minus this is going to be 8 over 6 times infinity squared. Again, that's going to be 0 plus 8. And I can see that my area is going to be exactly the same. Negative 8 over 3 minus 0 plus 24 over 3. And that's going to give me my area of 16 over 3 units squared. Okay, so these are, this is giving me the exact same areas I did here. This is quite unnecessary for the most part because we're going to use an integral to do this. But this is similar to going from the getting a derivative by using the definition of the derivative. Now, we don't do that normally. We just use define derivatives and power rule. With when we're doing this here, we will rarely need to actually work out the area using a limiting the Riemann sum as n goes to infinity. And the reason is because this is quite difficult because we do need to have summation formulas to be able to do this. So we only have a few here that we've established, and for more complex expressions, we would need much more complicated summation formulas.